Hey folks. Getting it started here, folks, with the next lecture. All right. Kind of feel a little weird with some animal collective this morning, all right? Okay. Let's get it going. Okay, so I just want to review these learning goals that I went through in the last video. So I noted that there is a lot of learning goals in this section. This is a pretty massive section. That's why it's over the course of 2 weeks. Okay. So let's see here. Find my highlighter. Okay. So we talked about learning goals 1 through 4 in those first 2 lectures I recorded on this section. In the first lecture, so lecture 7 and lecture 8, we talked about the equations for expansion work against constant external pressure of an ideal gas. So remember, it's just P delta V, right? Work is negative P delta V for expansion work against constant external pressure, which is the exact same as irreversible expansion, right? Okay, so know the equation. So that's the differential form of reversible expansion of an ideal or van der Waals gas. So this is still work equals negative PdV, and that's the differential form that I'm referring to. So being able to integrate P dV for either ideal gas or van der Waals. Okay, so know the relationship between irreversible expansion work and reversible expansion work. So again, that's noting that the irreversible expansion work requires you to just say a constant pressure times delta V. But the irreversible expansion work requires you to solve that integral. And then in the case of the ideal gas, you get negative nRT natural log of VF over VI. Okay? So know the various equations and be able to use them for constant volume heat capacities. So there was a lot of equations that I talked about for constant volume heat capacities. You don't have to memorize them if you know how to apply the degrees of freedom, right? So heat capacity for a solid is 3R. Heat capacity for a nonlinear gas is also 3R, and so forth. So be able to comfortably navigate through all of those. Okay, know the difference between constant volume heat capacity of solids, liquids, and gases. All right, so again, that's kind of also related to that same learning goal, just knowing the various equations, and also understanding that in the heat capacity of solids, I just talked about simple atomic solids being 3R, and I'm not going to really go beyond that for the scope of this course. And I just talked very briefly about liquid water as an example of a heat capacity of a liquid. So more on heat capacities today, and still noting the difference between heat capacity of gases, liquids, and solids. Okay, and then where we're going to pick up today is, as you can tell, enthalpy. Okay, so let's get that going. Okay, let's get that stuff out of here. Okay, so in the introduction of enthalpy, we start by recognizing that delta U, so the change in internal energy, is not equal to energy transferred as heat when the system is free to change its volume. Okay, so we noted that as a review, delta U equals QV. So when the system has constant volume, the change in energy is just equal to heat, right? So we always know the first law is Q plus W, but when the system is constant volume, that goes to 0. However, when the system is free to change its volume, delta U is not equal to this energy transferred as heat. So we have to use enthalpy. And we note that enthalpy is a capital letter state function. Okay, so what I'm going to prove to you now is that dH equals dQ at constant P for infinitesimally small changes, or for measurable changes, delta H equals QP. So that's the constant pressure heat. Okay? So I'm going to do a derivation to prove that. All right? And so what we're going to do is impose that we can tend H from H to DH, and U can go from U to DU. So this is just setting up that we can talk about all of our variables and their infinitesimally small changes. Okay, so that should be a dV. Okay, so this is just now going to allow me to expand this equation into the following. H plus dH, and by the way, this is the definition of enthalpy. I think I missed that. So when the system is free to change its volume, enthalpy is the internal energy plus an additional work term, right? We recognize P times V gives us work, okay? So now I'm going to expand this relationship to include the infinitesimally small changes of each variable, okay? So H plus dH equals U plus du plus P dP times V dV, okay? And so now, when I go ahead and expand on that, I've got H plus dH, U plus du, and now I have to FOIL this thing, okay? And by the way, I expect that this was probably not an obvious step to make, all right, not obvious. But as we kind of move forward in this course, right, we're going to apply the definition and rules of calculus to try and make sense out of things, okay? So this is like an instructor assist here. So if I go and FOIL this, right, first, okay, gives me PV. Outside gives me PdV. Inside gives me dPV. And last gives me dPdV. And now I kind of have to sort out what to do with all of this stuff, okay? Well, first thing to recognize, dP times dV, we're going to assume that tends to 0. And the reason why we're going to assume that tends to 0 is because that's two, I'm just going to write infinitesimally small changes, okay? So it's two really tiny numbers being multiplied by each other. So we're just going to effectively drop it to 0. It's not totally equal to 0, but within, you know, most of a reasonable number of sig figs, two very small numbers being multiplied to each other will drop out to 0. Okay? I'm also going to impose constant pressure right here. And the reason why I'm going to impose constant pressure is because we've already explored what happens when we impose constant volume. And so now the game to play is to hold the other variable constant, which hopefully by the end of kind of this whole section, it will be obvious why we play that game. Why we fix one variable and see what happens, then we fix the other variable and see what happens. So when I impose constant pressure, that means I think I wrote something, so I've got, okay, let me check my terms. I just realized I think I did something wrong. PV plus PdV plus, oh, okay, I see what I did wrong here. Maybe some of you caught that. So that term should have been VdP. So first outside, inside. So that inside term should have been VdP. And because I'm imposing constant pressure, I'm also going to say that dP drops that term out to 0. And so what I'm left with is the following. And I should recognize that U plus PV, okay, this one and this one, U plus PV is just H. Beautiful. Okay, so let's take that up to this side. And now, of course, what I can do is cancel H, and then, of course, the U and the PV, right, all canceled out. So now I have dH equals du. So du plus p dv. Okay, great. And so now from here, I always have to remember the first law and any other relationships that I know. So for example, I know that du is equal to dq plus dw. But I also know that work equals negative pdv. Okay, so substituting then that in, dw equals negative pdv, right? The differential form, okay? So then now substituting all that, I can say dh equals dq, and then I recognize that dw here was negative pdv, but then I have a positive pdv, so that all cancels, and what I'm left with simply is dh equals dq, and of course I'll put a little p there to indicate that that was constant pressure. Okay, so not obvious that enthalpy will equal the constant pressure heat delivered, but we get that from doing this derivation. Okay, and so now I like to kind of refer to these as the twins. Okay, so let me change color and let's talk about what I mean by the twins. So we know that du, change in internal energy, must be equal to dq at constant volume, and dh equals dq delivered at constant pressure. Okay, so these are nice relationships to know, the twins, okay? Enthalpy and energy. Okay, so I'm going to go back to changing color, and then let's see, let's move on to the next slide, okay? And so now we can begin to talk about the same processes we talked about before with constant volume, but rather at constant pressure, okay? And so by definition now, we have the constant pressure heat capacity, Cp, which is the partial of H by the partial of T at constant P. So remember to not mix this up with Cv, which is the partial of U by the partial of T at constant V. Okay? So as we move forward in this class, we're going to see a lot of these partial relationships. And eventually I'm going to have a nice acronym or mnemonic for us to remember all of these relationships. Okay, so in the same way that I could expand this relationship, I could expand this relationship of partials. And I can simply say that, well, dH has to equal Cp times dt. Okay, so I can just do algebra with these partials, right? And this is for infinitesimally small changes. And of course, for measurable changes, right, in experiments, delta H equals Cp times delta T, okay? Where the delta, again, indicates state function, final minus initial, all right? Oh, and then, so that is not supposed to be a U right there. That's supposed to be an H. So if we look at H versus T, we're going to see a very similar relationship that we saw in U versus T, right? If I expand this over some really large range, like a, 0 Kelvin to like 10,000 Kelvin, there's going to be some kind of like curvature, right, in this relationship. However, over a very, narrow range, and narrow range, right, that's hand wavy, that's kind of qualitative. There's some range, let's say, between, let's say, A and B here on this graph, where the constant pressure heat capacity, where this slope is fairly constant. I know that's not a very good line that I drew. But, right, so the slope of this line will give us that constant Cp. Okay. So as it turns out, we're far more sensitive to CP in the lab when we're doing measurements, because it's very difficult to actually fix the volume of something, okay? So even a liquid or a solid, we talk about those being incompressible fluids. As it turns out, as we're going to talk about in this section, you can change the volume of a solid and liquid just ever so slightly, okay? But on a gas, obviously, the volume will change enormously with changes in temperature and pressure. And so it's actually much easier in the lab to maintain constant pressure than it is to maintain constant volume, right? We're not doing our experiments up on a space station or whatever, or going like up and down in the altitude where pressure is constantly changing. When we're in the lab, pressure is usually constant, okay? But as far as CP and CV for liquids, I'll write that out. So as far as CP and CV for liquids and solids, they're roughly the same. Are very similar. And the reason for that is because, again, I noted that we can change the volume. We can compress or expand a liquid or a solid just ever so slightly. But because it doesn't change by very much, CP and CV for liquids and solids will basically be the same value. However, CP and CV for gases will be different, okay? And so now the final thing I'll take note of on this slide here, this is an empirical formulation for CPM, so molar heat capacity, right? Which would be, CPM, right, is CP divided by number of moles, okay? So this is an empirical formula where A, B, and C are fit parameters. And this allows us to actually calculate CP with variations in temperature. So if we wanted to expand CP over this really wide range, okay, we can look up these values. And so there's lots of these values for a given, liquid, solid, or gas, okay? And we'll play with this relationship more in the computer lab activity, okay? So moving forward. So here's an activity. So I just discussed how CP and CV for liquids and solids are very, very similar. However, I'm not going to show this derivation, at least not yet, but it can be shown that CP minus CV equals NR, or CP minus CV just equals R, which is really cool. Or another way to think of it, CPM equals R plus CVM. So spend just a moment, discussing or thinking to yourself, why is CP greater than CV? Okay, so you notice it's greater by one value of R. So it's greater by 8.314 joules per mole. So why is that? And what is the significance of that 1 unit of R? So see if you can kind of qualitatively or conceptually wrap your heads around that. Okay, so go ahead and pause the video if you need to and think that through, or I'm just going to turn to my cheater notes here so I give you the answer correctly. Okay, and so the significance, the reason for CP being greater than CV is because most systems expand when heated, particularly at constant pressure. Okay. So such systems will do work on the surroundings, right? So as something is expanding as it's being heated, it's doing work. It's doing work on its surroundings. And so therefore, some of the energy supplied as heat has to escape back out to the surroundings. And so as a result, the temperature will rise less rapidly than if it were not free to expand. Okay, so that means CP is greater than CV because if you're allowing that system to expand, you have to be pumping more heat into it to fuel that expansion. Okay? So hopefully that makes sense. So conversely, CV is less than CP, right? So I could write CVM equals CPM, of course, minus R. So CV is less than CP because when volume is being held fixed, there's no expansion work that requires an input of energy. Okay? And so what's the significance of 1 unit of R? 2 degrees of freedom. Okay? And what are those 2 degrees of freedom? Well, those 2 degrees of freedom are either changing the volume or changing the pressure. Okay? Which I realize is a little bit different than the ways we talked about degrees of freedom before. And that landscape of either being able to change pressure or being able to change volume as degrees of freedom, we'll talk about that more when we discuss phase equilibria in the coming chapters. Okay? And so notice that this is just for an ideal gas, right? So we'll have some other things to talk about if the gas is not ideal, and some even further things to talk about for monoatomic gases or linear gases or nonlinear gases. Okay? So this is a good relationship to know. Okay, so moving along. So now I'm getting into section 2.6 here in Atkins, which is all about adiabatic changes. So thus far, we've discussed either constant volume processes or constant pressure processes, which basically result in the case of constant volume, no work being done. In the case of constant pressure, there is work being done in addition. However, that work ends up being zero, right? dH ends up equaling heat at constant pressure. So now let's discuss adiabatic changes. And for adiabatic changes, we know dQ equals 0, so there's no heat exchange between system and surroundings when something is adiabatic. All right? And so that means if we are looking at, let's say, a temperature versus volume curve, now if we're changing the temperature and volume of something, the work done, okay, matters. And as you might also note, because temperature is changing on this scale, when something is adiabatic, it can't be isothermal, okay? So there has to be an accompanying temperature change, can't be isothermal. So there has to be an accompanying temperature change when something expands adiabatically, okay? And so it can be shown the following relationship. If I change the volume of something from VF to VI, okay, then there has to be a temperature change from TI to TF. And it's related to this relationship where TF equals TI times the ratio of VI over VF. And I know this kind of looks goofy the way that this constant is written. I just want to be consistent with the book. So that's what the book is showing, okay? And when we imagine moving down this line, changing temperature and volume, right? A good way to think of this is kind of like as a vector, right? That this is motion in 2 different dimensions on this space. There's motion in this direction at constant t, right? So if you move along this line, so u is a constant when the temperature doesn't change. But then now there's motion along this line at constant volume, where there is a change there, okay? And so number 1, you know, u is constant. And number 2, you notice that this says delta u equals CV delta t, because along this line right here, that's a constant volume line. So we can call up this equation for constant volume. Okay? So how does this all work out? How do we, so I want to derive, let's see what I have on the next slide. Yes, okay, so I've got plenty of space here to work. So now I want to work out so this is again another one of these scenarios. Let me rewrite that. And this scenario, reversible adiabatic expansion of an ideal gas. So we're adding lots and lots of qualifiers, right? We've already talked about reversible expansion. We know what that's all about, okay? So reversible expansion is PdV, right, where I have to actually integrate the P, okay? And adiabatic, we recognize adiabatic refers to the following: du equals dq plus dw. So because it's adiabatic, dq has to be 0. And thus, du equals dw. Okay? Well, what other relationships do we know? Well, I'm going to make a little inventory over here on this side. We know that dw equals negative p dv for reversible changes, for reversible expansion or compression. We also know when volume is being held constant, okay, du equals cv dt. Another relationship that we know that um equals 3/2 RT, but that doesn't really do anything for us because we don't see any volume dependence. So now what we can say, okay, I've got du equals dw. And by the way, this is another like pretty challenging derivation, so instructor assist, right? I wouldn't expect you to be able to just come up with this. So if we know du equals dw, then I can say, let's see, I lost my train of thought here. Oh, yes, okay. So then I can say cv dt equals negative pdv. So I got that by saying I know du is cv dt, and I know dw is negative pdv. So I write that down, okay? And we're dealing with an ideal gas. Oh, yeah, so another equation that I know is nRT over V, okay? And I'll go ahead and make that substitution. cv dt equals negative nRT over V dV. And now I'm cooking. And I'm cooking because, look, I'm interested in changes in temperature, dt, with changes in volume, dV, right, to get the slope of this line, okay? And there we go. I've got a dt and I've got a dV. So I know I'm on the right track. And what I'm going to now do is combine all like terms with all like terms and say cv dt divided by t equals negative nr divided by v dv. And so now what we can do, so this process I like to call divide and conquer. So we divided, and now we're going to conquer. And the way that we conquer this thing is by integrating both sides. So cv dt over t equals negative nr over v dv. So I integrate both sides with respect to their variables, okay? And so what I get, and so of course I'm integrating those right from, I'm just going to say I and F and I and F, and we recognize that this would be Ti to Tf, and this would be Vi to Vf, okay? So dt over t gives me natural log, right? And the constant Cv, we'll just assume that it's constant over this temperature range, okay? So putting this over here, we've got now Cv times natural log of Tf over Ti. And then now dV over V is also a natural log relationship. So I'm going to get negative nR times natural log Vf over natural log Vi. Okay. And then now I'm going to do a couple of log tricks. Okay. So I'm going to divide this over to this side and say that that's Cv over nR times natural log of Tf over Ti. I'm also going to do, so that was just algebra. I'm going to do a log trick here, and that negative sign I'm going to absorb into the natural log, which makes this ratio flip. So now that just becomes natural log of Vi over Vf. Okay, I'm going to call all of this stuff, right, lowercase c, okay? And there's another log trick that I can do, and that log trick is when I have something in front of a natural log, I can raise it to the power in the log itself. So I can now say natural log of TF over TI raised to that constant C equals natural log of VI over VF. And I ran out of room. However, hopefully you can see, right, the way this is going to go. So if let's see here. Yep, so if I take E of both sides, then I'll get TF over TI equals VI over VF raised to that constant C. And then now the algebra, right, I'm not going to finish this because I don't want to write a bunch of sloppy stuff, but see if you can finish the algebra and arrive at that relationship from there. Okay? So let's see what I have on the next slide. Okay, so this relationship, this gives us this curve here. So this gives us a way of predicting what is the change in temperature when we have expansion of an adiabatic system. And so how, physically wrap your head around what's going on there, right? So imagine you have a gas and it's in a container, and that container is able to change volume. It's able to expand or compress, but that container is adiabatic. It's isolated. It doesn't allow the exchange of any heat. Okay? So what we would see as this adiabatic container is expanding, the gas inside has to cool down, right? You notice this relationship. So that's I and F, and this is I and F, initial and final. And so what's physically going on there, right? As the gas is expanding, it can't acquire heat from the surroundings, so it has to use its own heat to fuel that expansion. That's why the temperature decreases in the expansion, in the adiabatic expansion of a gas. Okay? So the same relationship that I'm talking about right here can be written in another way. Okay, keep note of how this goes. TF equals TI. If I multiply the constant through and set this up in kind of like a Boyle's law or a Charles law kind of a way, right? You can write this as, so this, I wrote that as PF and VF, but I think V and T is what I meant to write. Okay, so sorry about that. That should be T, and that should be T. So let's rewrite that. So that should be T final times V final. And I'm going to raise this, I'm going to put a new exponent in there, okay, that we're going to talk about now, equals TI. Yes. Sorry, I'm just checking to make sure I get this written correctly. Yes, equals TI times VI raised to this constant gamma. So I did a little bit of extra algebra here that you can follow through on the book if you want to see where it comes from. But this is basically another way of talking about this adiabatic expansion. Or like if we were writing this in like a Boyle's law, Charles law kind of way, we can say TV raised to some constant is a constant. Or in other words, T is proportional to 1 over V. I'm gonna erase that C and use the gamma to be consistent. That's a Greek letter gamma. So what this also means, T is proportional to 1 over V raised to this little gamma. So note, compare that to Boyle's law, which says T is just proportional to 1 over V. Okay, so now what we have here, this is what we call an adiabat, which you can see indicated by this blue line. And so this is giving it to you in terms of P, but we could also draft this up in terms of P. Okay, so I said T is proportional to V, T is proportional to V, But we could also, I think that's why I confused myself. We could also write this in terms if we were fixing the other variables, right? Isotherm adiabat. Sorry that that's confusing. Okay. So, yes. So now what we can see on this three-dimensional scale here, just playing around with these adiabats and isotherms. So the isotherm is going at constant temperature, right? So you notice on this three-dimensional curve, it's just any one of these slices, right? Any one of these slices could be an isotherm, okay? But an adiabat, on the other hand, so those are probably going to get confusing to see. An adiabat, on the other hand, because it has this exponent right here, it's 1 over v raised to some power gamma, which now I'll talk about. Gamma is the ratio between Cp and Cv, okay? All right, so whatever Cp and Cv is, you can tell we would still have to plug in an equation for Cv, an equation of R, and we're going to do that next. All right. This means that adiabats fall off steeper. They have a steeper slope when you look at this at a two-dimensional graph, right? So you can see on this two-dimensional graph, the adiabat has a steeper P versus V relationship than the isotherm. And that's, again, because of these additional degrees of freedom that are required to be populated throughout this expansion or compression. And so depending on whether it's a monatomic gas, linear molecule, or nonlinear molecule, the adiabat may fall off even steeper depending on what this fraction gamma is. Okay? So sorry this was confusing with the P's and the T's and the T's and the V's, right? It's just like using our gas laws the same way we did before. If we know we can fix one, we can talk about the relationships of the other, okay? But it's important to note adiabats cannot be isothermal, right? You notice on this three-dimensional graph, it is changing temperature. Okay, so let's do an activity. What is the value expressed as a fraction of gamma for a monatomic ideal gas, for a linear molecule, or a nonlinear molecule? So I'm going to put this relationship up here again. CPm equals CVm plus R. We note that gamma equals Cp, I'll just write Cp divided by Cv, CPm divided by CVm, same thing. So you can work through these with me if you like. Otherwise, I will play some music and work through them myself. Okay? I love this song. I could listen to this all day. Okay, folks, let's go ahead and talk about this. So hopefully this was fairly straightforward. And you remembered that CV for a monatomic gas is 3/2 R. CV for a linear molecule is 5/2 R. And CV for a nonlinear molecule is 3 R. So these each have an additional whole unit of R for CP. And thus that gives you gamma for a monatomic gas is 5/3. I'm just going to express that as a decimal real quick for a quick comparison. So that's 1.67. We get gamma for a linear molecule is 7/5. So that's 1.4. Okay. And so we get that for the linear molecule, it's 4 divided by 3, which is 1.33. So the trend is there, that the value of gamma is decreasing with more degrees of freedom. Okay? And so the physical interpretation of that is on this curve, on these adiabats, the monatomic gas will fall off much quicker. So it's going to have a much steeper change in volume with pressure. And the reason for that is because it doesn't have as many degrees of freedom that need to be supplied with heat in order to fuel that expansion. Okay? So in other words, the nonlinear molecule, before it can even do any of that expansion work, that heat has to either get pumped in or pumped out of those degrees of freedom before any change can happen. Okay? So hopefully that makes good physical sense to you. If not, we can most definitely talk about it more during office hours or during our live session. Okay? So now I think that this is a good time to stop. So you can see on the next video, we're going to talk about thermochemistry and standard enthalpy changes. So hopefully that will be some familiar ground for you all. Okay, folks, I'll see you in the next video.